Okay, so let's keep talking about equilibrium. So in our last section, we learned how to write the equilibrium constant expression, which was either Kc or Kp. In this one, we're going to talk about what does that K value tell us about the reaction. So what you may have noticed from the expression is that the K value is actually a ratio of products to reactants. So in your POGL you did last week, you were looking at that ratio. So you actually know what that K value means. You just didn't know that that was the K value that you were calculating. So if K is greater than 1, the reaction is product favored, meaning the product predominates. So when we're thinking about what the K expression is, it's the products over the reactants. So basically what we're saying is if it's greater than 1, the top number has to be bigger. So that means that there's more products. So that means that if we were to kind of like draw a bigger arrow, that the reactants, that forward reaction, is going to happen with a higher percentage than our reverse reaction. Now the opposite is true. If K is less than 1, the reaction is reactant favored, meaning that it had a, let's do that in red, it's reactant favored, meaning that your denominator was greater in order for it to be less than 1, and that the reaction proceeds in the reverse a little bit higher than it does in the forward direction. We can say that for K greater than 1, the products are favored or the reaction lies to the right of the equation. We can say the opposite for less than 1. The reactants are favored or it lies to the left. Okay, so when we manipulate these equilibrium constants, we can do a few different things with them. So if we're looking to find the Kc for the reverse reaction, so one thing we need to know about the equilibrium constants is that the way that we write them, reactants or products over reactants, we are writing an equilibrium expression for the forward reaction. So when we look here, our reaction is N2O4, and then our products are two NO2s. So we would do products over reactants, and we get a value of 0.212 at 100 degrees Celsius. So if we want to look at the equilibrium constant for the reverse reaction, we would flip the reaction, and now we have 2 NO2 in the reactants and the N2O4 in the products. So basically what we've done is flip the reactants and the products, and so we have a totally different value. And so the way to get that is to take the reciprocal. So we can do 1 over 0.212, and that is going to equal the 4.72. So we're flipping the reaction. So if we look at this reaction, it's run at 25 degrees Celsius, and our Kc is 1 times 10 to the negative 30th. So this is a really small value, which tells me that in this, the reactants are favored. That negative 30 there tells me it's a period, 29 zeros, and then a 1. We're going to use this information to write the equilibrium constant expression and calculate the equilibrium constant for the basically reverse reaction. So our expression is going to be the products N2 and O2 over the reactants NO, and then remember that coefficient becomes an exponent, so squared. And then to find the Kc for this, it's going to be 1 over the forward one. So it's going to be 1 times 10 to the negative 30th. Now, if in the forward reaction the reactants are favored, I would assume that if we flip the reaction, the products should be favored. So I'm expecting this to be a number greater than 1. And it is much greater. 1 times 10 to the 30th, meaning it is product favored now. Okay, so that's one way that we can change the equilibrium constant. So now I want you guys to try it. We're looking at KP. KP is going to follow the same rules. So for N2 plus 3H2 gives us 2NH3. What is the value of KP for the reverse reaction? So right now when I'm looking at this, that -3 tells me that it is reactant favored. So my reverse should be product favored. So I'm just going to do 1 over 4.34 times 10 to the negative third. And I get 230.4. Remember, K doesn't have a value, but it's greater than 1, so that tells me now it is product favored in the opposite direction, which is what I expected. Okay, another way that you can manipulate the equilibrium constants is by multiplying the whole reaction by a value. So we kind of did this with Hess's law a couple chapters ago where we said, okay, if we double the reaction, what does that do to, I think we were looking at enthalpy values or entropy values. This one is slightly different. So if you double the number, so if we go from 2 to 4, remember you guys that 4 value we're not multiplying by 4, we're raising it to the power of 4. So when we double the equation, it actually raises it to the second power. So what we end up doing is taking this whole thing and raising it to the second. And so it ends up being 0.212 squared. So our new one is 0.0449. So we haven't flipped the equation at all. We just doubled the coefficients. If you tripled the coefficients, it would be like raising it to the third power. Or if you quadrupled the coefficients, it would be like raising it to the fourth power. So however it changes from the first reaction to the second, that is what you raise your expression to. So how does the magnitude, and when I talk about magnitude, you guys, I'm talking about the size, okay? So how does the size of the Kc for the reaction 2HI, H2 plus I2 change if the equilibrium is 6HI, 3H2, and 3I2? So if we look, we're taking our first coefficient from 2 to 6. So that is times 3. Let's just make sure it's consistent the whole way. We're going from 1 to 3 and 1 to 3. Okay, so we multiplied by 3 to get from our first equation to our second equation. But our Kc is going to be raised to the third power because remember we take the coefficient and we raise it to that power. Okay. The last thing that we can do with equilibrium constants is basically put them together like we did with Hess's law. So we've seen kind of all of these ideas before. So the equilibrium constant for a net reaction made up of 2 or more steps. So if our reaction mechanism is more than one step, we are going to take the product of the equilibrium constant. So in math, when we say product, we're saying multiply. So if we have a multi-step process to find the overall equilibrium constant, we're going to multiply those together. So we're going to calculate the equilibrium constant for the overall reaction from each individual reaction. So if we look at this problem here, Br2 would be our intermediate molecule. And so we're looking at 2, our overall equation. It's going to be 2NOBr plus Cl2 gas, 2NO, and 2 BrCls. And I just want to make sure it's balanced. So I've got 2 NOs, 2 NOs, 2 BRs, 2 BRs, 2 Cls, 2 Cls. Okay, so we did it correct. So now we added those together, but our Kc values we are going to multiply. So the Kc of the whole thing is 0.014 times 7.2 and that is 0.1008. And again, the equilibrium constant expression does not have a unit. So let's do a quick review. So when we manipulate them, and this is, if you need a little bit more work with this, it's all summarized on page 622. So in a reverse reaction, the equilibrium is the reciprocal, or 1/, of the forward reaction. If a reaction has been multiplied by a number, the equilibrium constant is changed by raising to the power of that number. So if Kc squared would be from 2 times the equation. And then the last one we just did, equilibrium constant for a net reaction, is the product of the individual reactions. Okay, so you guys will have a couple of problems to practice these skills in Google Classroom.